Thank you, Sakura, and thank you, the organizers, for putting together this great conference and having me here. So I will talk about this joint project with my postdocs from the Simons collaboration, Monique Mueller and Hector Martin Peña Polastri. And Hector will be applying for jobs. He's great to work with, and he also knows some physics, so just saying. So as a disclaimer, before we start the talk, this talk will be, as you can see, the start in the math world. So I don't think I will say any physics word, but I thought that maybe this is a great place, so then some of you can help me to have some extra stars here, maybe here, something. So if you see something interesting and want to talk after the talk with me, that will be great. So maybe let me tell you a little bit about the motivation. And if you have heard me about fusion categories before, I already said it. Fusion categories is kind of a young field in math, and we're still looking for exciting examples. And one way to get there is through new constructions. So in particular, these exact factorizations are new constructions of fusion categories. And there are kind of two ways to see these. One would be I have a fusion category that is or any other algebraic object, right? A complicated algebraic object, and I would like to decompose it and see if I can understand it in terms of simpler ones. Or in the opposite side, maybe I have already some well-known fusion categories and I want to create a new one that maybe gives me more interesting properties or things using the ones that I know. So that's kind of the idea that I will be thinking about with this construction. So I will just give the definition more or less quickly of fusion categories. Probably you already saw it many times, but just to fix some notation. So when I will be talking about fusion categories over the complex numbers, I will think about C-linear categories. So I have basically all what I want to be able to have exact sequences, like direct sums, a zero object, my maps have kernels, co-kernels, these kind of things. And moreover, the space of maps, the space of morphisms, is a vector space over the complex numbers. I want some properties on this abelian C-linear category. So in particular, I will ask my category to be semi-simple. Every object can decompose as a finite direct sum of simple ones. And I want this finiteness condition that, since I already asked for semi-simple, I can cheat a little bit and tell you that basically I want these home spaces here to be finite dimensional, and I want to have only finitely many simples up to isomorphisms. So that's what I will be thinking for finiteness. But then I want this extra structure, the monoidal structure, so I want to have the tensor product, the associativity, my unit object, and I want some properties on it, so I want to have duals. I want my category to have duals for every object, duals in this categorical notion, in this categorical setting of having an extra object in the category that has evaluation, co-evaluation, and satisfies some axioms. And then kind of a compatibility condition between my two structures. I have the linear abelian structure and the monoidal. So the unit is a distinguished element in my monoidal category, and I want this to be a simple object in the sense of abelian categories. So that will be kind of a compatibility. So some examples to keep in mind are the category rep G or the category rep H for finite dimensional semi-simple Hopf algebra. So that are examples on how I started studying fusion categories actually. Then we have vec G omega, these finite dimensional G-graded vector spaces with this associativity given by the cocycle. And there are many more, but one nice example, and I will mention it later. So it's these Tambara-Yamagami fusion categories. One example that probably you all know is the Ising one. So that's Tambara-Yamagami when the group is Z2, and it's the only Tambara-Yamagami that it's a modular category actually. So these are all some examples, and there are many others. So how I will be thinking about this exact factorization, how I will be thinking about these fusion categories, I will have my fusion ring and my F symbols or my associativity constraints. So I will be thinking about this fusion or Grothendieck ring and trying to understand how it is in this setting, and then trying to see what associativities I can put on it. Okay? So before giving you the definition in the categorical or in the fusion categorical setting, I want just to remind you of some things that maybe you have seen for groups. So there are two notions, and maybe the first one is, maybe you have seen it more, the notion of extensions of finite groups, and also this notion that I will be talking about today of exact factorization. So we have exact sequences of groups, like this one, and we have a notion of an exact factorization, and as I wrote there, it's just a factorization of my group that has the two subgroups having trivial intersection. And then in 2010, Bruguière and Natale generalized or gave a fusion categorical notion of exact sequence of fusion and tensor categories. And that one was a very nice and natural notion if you think generalizing the exact sequence in the setting of groups or in the setting of Hopf algebras. But actually, later, Ettinghoff and Jellaki generalized that definition, adding the possibility of having a module category involved. So there are some exact sequences of fusion categories with respect to a specific module category, and why that was necessary, because in the notion by Natale and Bruguière and Natale, one of the categories, because of the definition, was mandatory Hopf algebra, or coming from Hopf algebras. There was a fiber functor. So what they did is change that condition. Instead of asking for this fiber functor, they changed the category, the module category, to be anything instead of just Beck. That's why there are two definitions. And in 2016, Jellaki gave the definition that I will be working today with of exact factorization of fusion categories, and a little later, Basak and Jellaki show that there is a one-to-one correspondence between these two things. So I before mentioned another definition that later I will mention again, but so what is an exact factorization of a group? You have that for two subgroups H and K, any element in your group can be written in a unique way as a product of an element in H and an element in K. So some known examples are the direct product. Also, in the case of the semi-direct product, this happens. And maybe an example that is known of this is the symmetric group in n letters, that you can write it as an exact factorization of the symmetric group in n-1 letters, thought about this subgroup as the maps that fix the last one, the n place, and the cyclic group as the one generated by this cycle. So as I mentioned before, there are many, that asterisk there is to say that there are many equivalent definitions as the one that I gave before of having that the group is a factorization and the intersection of the subgroups is trivial, or another way to say that is that the intersection of the groups is trivial and also the order of the group is given by the product of the orders of the subgroups. I'm mentioning this because that will help me in the various definitions of exact factorization of fusion categories. But the idea, or one way to think about what is an exact factorization is that you have the Cartesian product of sets of the underlying sets for these subgroups H and K, or for two groups H and K, and I want to know what are the possible group structures that I could put in this set. So that's kind of the idea. So for groups, this was well studied, and one natural question is asked, okay, I gave you some examples, but how can I construct more examples of exact factorizations of groups? And for that, there is this auxiliary notion of match pairs of groups. So what will be a match pair of groups is two groups H and K coming with some actions, some group actions. But what is important is that these group actions don't need to be actions by group automorphisms. It just need to be actions. So what I want to know, or we will ask for some condition, we will ask for some compatibility. Instead of being group automorphisms, we will ask for something going on here, what's happening. So what we will do is something similar to what you do in the semi-direct product. And what we will request is, okay, let's say that I want to act on this. Okay, this one is next to this one, so I will just act. But to be able to act with K in H prime, I need to pay a price. And what price I pay? That this one acts on this one. And I have the same equation, but symmetrically turned for the other one. So that's the idea. So as you see, it's kind of a generalization of what can you imagine for the semi-direct product, and I will say that in a minute. But okay, we are introducing this definition. We have these two groups, these two groups actions that define this, but why I introduce this is because I want to give you associated to this some interesting group, right? So I will do that. As I told you, as a set, I will think of this group just as the Cartesian product of sets. And now I need to tell you what's the product. And again, think about what you do for the semi-direct product, and now you will do it in both sides, because now we have actions in both sides. So originally, if it were the direct product, I would like to multiply this together and this together, but I need to pay some price because they are not next to each other. So what I do is I will act on this one to let it go to the other side, and act on this one to let it pass to the other side. Okay, so it's a double semi-direct product, basically, okay? And if one of the actions, it's by group automorphism, if one of the actions is trivial, the other will be by group automorphism, and you will recover the semi-direct product. So that's why it's also an example. But okay, we constructed a new group, and actually one can prove that this is indeed one of the examples that we wanted, so matched pairs were useful, we did what we wanted, we construct an exact factorization, okay? So now you are able to construct some, but we would like to know, okay, but is this a good construction? Are these all of them? Can I find more exact factorizations of groups? And the answer is not. If you have an exact factorization, there need to be, this is if and only if there is some match pair associated to it, and you can prove that the group is isomorphic to this bicrossed product. So basically, bicrossed products of group give you all the exact factorizations. Okay, so this was the kind of warm-up. Now we will go to this definition by Jelaki. Actually, the one that I have in the slide is not the first definition he gave, but he proved that many definitions are equivalent, and I will present to you the ones that are more handful to work with. So you will see that this is somehow similar to the definition for groups. In group, any element could be written in a unique way as a product of elements in one, or in the first and in the second groups. Here, it will not be for any object, but for any simple object in B, there exist unique simple objects in A and C respectively, so that my simple in B is a tensor product of these simples, okay? So one remark, and this is also true for groups, but I didn't point it out, is that actually, if I have that B is an exact factorization of A and C, it's also, or this is if and only if, it's an exact factorization in the other way. In this definition might not be that obvious because the order of the tensor product matters, but one equivalent definition is using something more similar to the one that I told you about the order of the group. So if you have that your two fusion subcategories intersect trivially, meaning that the intersection is just the category of vectors, finite dimensional vector spaces, and the Frobenius-Perron dimension of your bigger categories, the product of the Frobenius-Perron dimensions of your categories, that's also giving you that B is an exact factorization of A and C, and this definition is clearly commutative, so it's more easy to see the remark coming out from there. And both of these definitions are very, very useful combined. That's what we use a lot to prove everything, and I will mention maybe where later. So maybe let me give you a couple of examples. As you might imagine, the linear product is one of these. Then maybe you are familiar with this construction of this cross category, sometimes called, or this semi-direct product. This is also an exact factorization of fusion categories. And this is a nice one because it's dual to the equivariantization, so it's interesting. It's more equivalent to the other one. So then one question that Jelaki answered is, okay, what are the possible exact factorizations and how they relate in the case of groups, right, with vec G omega? And what happens here is that if you have one of these pointed categories, it will be the exact factorization of two pointed categories, and the group need to be an exact factorization of the groups, and the cocycle need to satisfy some nice restriction, okay? But then, for example, Tambari-Yamagami is never an exact factorization, at least a non-trivial one, okay? A comment that I wanted to make for groups, and I forgot, and I actually had an asterisk, but I still forgot, is that for groups, for groups, you cannot ask one of the groups to be trivial, or at least in the definition, that's not allowed. We allowed one of, in the exact factorizations of groups that I will use, I will allow that, but in general, they don't. Yeah, I have a question.
In the vec G case, Is omega uniquely determined by the condition on the slide?
No, I don't think it's uniquely determined. I think there could be a couple of.
So if I specify omega 1 G1 and omega 2 G2, and I do this product on the right-hand side, is the left-hand side unique?
In principle, I think it's not unique because you could have different omegas that restrict well, and maybe a little bit later, or maybe I can say now more or less. But I think by extension theory of ENO, it shouldn't be exactly unique. Maybe there should be some co-cycle multiplying that let you change it. It will not be unique, but maybe unique up to a torso, like up to a co-cycle.
So unique as a cohomology class?
I think you will be able to multiply by an extra co-cycle and move it.
Thank you.
And I will mention more about this if I have time at the end of the talk.
So if that's the case, then, because I was going to ask what the relation of the centers, the Drinfeld centers is.
Okay, that's...
If the omega is then different, then
that's in my last slide.
Oh,
it's one of them, maybe. I mean, I will... Maybe in the last slide I say something about that, but that's a great question, Sakura. So maybe before giving you some results, I want to remind you or introduce for you some invariants of fusion categories that are very useful. And these ones are actually, or part of these ones are at the fusion rules level, some of the ones that I will be using. So a grading of an fusion category is this decomposition in abelian subcategories that are labeled by the group G, and they behave well with the tensor product. We will be looking at faithful gradings, meaning that we do want all components being different from zero. And Jelak proved in their paper about nilpotent fusion categories that you can always have one of these faithful gradings, and this is called the universal grading, and it's given by some group that is called the universal grading group. Why it's called universal grading group? Because any other group that faithfully grade your category will be a quotient of this one. So it's an important group defined with this universal property. And the trivial component of that grading is a very nice subcategory that is called the adjoint subcategory, and it's the fusion subcategory generated by X tensor X dual for X simple. Okay? So some examples, if we have our favorite example back G omega, the universal grading group is G, and the trivial component of that, the adjoint subcategory is Beck. For Tambari-Yamagamis, the universal grading group is Z2, and the trivial component is just the abelian theory, Beck A. Okay? For rep G, there are some also, and for rep H, there are also nice discussion about this in Jelak-Nikchik's paper, and it's related to the center and things like this. And another category that I will be mentioning is the pointed subcategory, so just the category, the fusion subcategory generated by the invertible object, so the simples that X tensor X dual give you the unit. So I will be looking at that. And why? Because I want to mention some remarks. I told you, okay, Tambari-Yamagami doesn't admit any exact factorization, or I told you, okay, the pointed category is decomposed in this way. Okay, all this follows from some remarks. The pointed subcategory, so maybe I didn't wrote it in the best order actually. This one is an important one. The Frobenius per round dimensions will be preserved for the objects in the category. And so if the category you started is pointed, so some things will be preserved in the categories. So if you have two fusion subcategories that are integral and you want, or if you have an integral category and you want to see if it admits exact factorization, the factors need to still be integral, the same for weakly integral. We proved, okay, maybe this I will mention later, but also this follows from this comment, because invertible is the same as having Frobenius per round dimension 1, so you will be obligated to this. And the groups that give you the Beck G omega in these cases will also, so the group of invertibles of your categories will also give you an exact factorizations of groups. Maybe one of the groups here is admitted to be trivial, even if in the original definition for group is not. But with Hector and Monique, we were able to prove, and this was a key part of the work that doesn't seem that interesting in principle, but was very, very helpful to then give some definitions. I think this was one of the key points, that the universal grading of group of B always, it's an exact factorization of the universal grading groups of A and C. when you have an exact factorization, and also the adjoint subcategories. And that gives a lot of restrictions. So basically what I'm saying, because all these are all Grothendieck invariant, are only things that depends on the fusion ring. All this actually depends on, or is exact factorizations behave very well at the level of the fusion rings. And what we did was, in many parts, work in the fusion rings to try to understand it and then try to lift and find possible associativity. So that's what we did. So what are the natural questions that we were trying to answer? We wanted to know how we can construct exact factorizations of fusion categories, maybe something like in groups. So this notion of match pair and bicrossed product. And as a spoiler alert, the title say that. So yes, we will be talking about bicrossed products. Then we wanted to see if it was possible to characterize the fusion ring of an exact factorization. And again, spoiler alert, I told you that the exact factorizations behave well under the Grothendieck part of your fusion category. And then we wanted to know if we are finding all of them or what's going on with associativity, which usually, as Kevin was saying, the fusion rules are usually nice and more friendly, and finding things that are Grothendieck equivalent is okay, but the associativity is usually a challenge. So let me tell you the answers we found. We were able to define a match pair of fusion categories, and here there are many asterisks because this was the very challenging part. And we were wondering, because the three of us, we come from Hopf algebras background, and there is a notion of exact factorization of Hopf algebras. There are match pair of Hopf algebras, there are bicrossed products. So the people working on this area were Jelaki and Natale, which are are experts on this topic. So we were wondering why it was not defined before. And when we were trying to define it, there are some challenges, and in particular, in principle, you would like to have some actions of a category on other. And that starts getting complicated, and that starts giving you some obstruction. So we couldn't do it in this way. But when we look at the fusion ring level and when we wanted to use a trick, we realized that actually we could define things that only depend on we did it first at the level of the universal grading group, that's why the first slide mentions that, but that the actions that we wanted to define didn't depend on the elements or the objects themselves, but the grading component the objects were. And that's how we came up with this definition. So here, the data for a match pair of fusion categories will be the following. I will start with two fusion categories that admits, here I should have written faithful gradings. These need to be faithful gradings. If I forget, all the gradings here will be faithful. And then these groups that are giving me the faithful grading will need to have attached to them a match pair of groups. So I want to have some exact factorization associated to that groups, or a match pair to be able to construct this categorical match pair. Then I want to have categorical actions, and now I'm fine because I have groups. I was able to find groups, and we all know how to define these categorical actions. And again, as in groups, I don't want these actions to be as strong as possible, which a lot of the time, for example, when we do equivalentization, I think we want actions by tensor autoequivalencies. Here, not. I don't want that. I just want categorical actions, so linear actions. And then I want to tell you how they will behave with respect with the tensor product. And if you see, it's a similar formula to the one that I wrote for groups, but there are a couple of things. First, I want these categorical actions to behave well with my gradings. That's kind of a not that expensive thing to ask. We want compatibility with the things that we already have, because these categories come with a grading. And okay, this is the condition I was saying is, because of this, it's not like group automorphisms or not by tensor autoequivalence. I want a little bit less, and I want them to behave well with the units. Plus, we have to ask for many diagrams, as you might imagine, but the diagrams are what you can guess if you try to write, okay? And so, of course, the next step is, I didn't have the match pairs because I like them only, but because they give me exact factorizations. So the answer is yes, we were able to define this bicrossed product in the same way as an abelian category is just the delineate product. We define the tensor product as a kind of a double semi-direct product. And the important part, and what I wanted to mention in part here, because I know that you like this, we have very explicit formulas for the associativity in terms of my categorical actions. These are categorical actions, so it comes with extra data, and this gamma and eta that are giving me not the automorphism, but this lighter condition. And we were able to prove that these are, give rise to an exact factorization, but we want it, so we answer the first one. I'm able to give you some examples, but basically we wanted to know if all the examples look like this. That was the main goal. So what we could prove first, as I told you, these are well behaved under fusion rules. So if you give me an exact factorization, there will exist some matched pair of fusion categories such that the fusion rules of my exact factorization coincide with the fusion rules of the bicrossed product associated to that. So we understand very well how the Grothendieck ring or fusion rings of this exact factorization looks like, and look like the ones that we constructed. So that's the second question, but what about the possible associativities? And that's a hard question. So what are the different categorifications that these fusion rings admit? What are the liftings? And let me quickly say, because I know I'm almost on time, that this is a hard question. Just starting to thinking about this example that Jelaki pointed out, the one of pointed fusion categories, if we really had everything, basically we will be close to understand very well the cohomology, the third cohomology for exact factorizations of groups. But already at the level of the direct product, it's not that easy. There exists this theorem that it's a Q-net formula. For semi-direct product, it's not always known. And so imagine that for exact factorization less. At the beginning, we were very excited. We were like, oh, we will prove this exciting theorem for groups. No, it's not that. Not like that. So one natural question is, okay, but is there at least a Q-net formula for fusion categories? So what are all the possible associativities that I can put in the Grothendieck ring of A tensor or A the linear product C? And this, Tinkovnichik and Ostrich are working on this, because at some point we thought that we were working all in the same thing, but they are working on this part. So hopefully they will have all the possible associativities soon. And that will be very exciting, because then I think we will be very close to have all things that are possible. Why? Because of extension theory. That is kind of what I was mentioning at the beginning when I was asked about this. So in extension theory, Tinkovnichik and Ostrich, they prove that if I have two extensions of the same fusion category, the same trivial component, and I have two different extensions with the same fusion rules, once I fix the fusion rules, there is not that much freedom. One associativity needs to be a multiple of the other, but the multiple is a cocycle. So there is not that much freedom. And basically, in our case, what's the nice thing is we know how the Grothendieck ring looks. We know that all exact factorizations are basically an extensions of their trivial component by this universal grading group that it's an exact factorization of the other universal grading groups. So we know that any other exact factorization would be, like the associativity will be a multiple by a cocycle. That again, I'm telling you this cocycle might be something hard, but at least we understand more or less how this works, of our associativity, of the one that we were able to construct with the data from a matched pair. And also we were able to prove how the trivial component of this, at least under the universal grading, how the trivial component of the bicrossed product looks, and it's actually the linear product. So combining with the Tinkovnichik-Ostrich, hopefully soon result about Q-net formula, we will be having all, at least in a theoretical way, using extension theory. And okay. So I will say very quickly, it's just these two things. This is one of the last results. We were able to prove that in some very extreme examples, we got everything. For example, an exact factorization of Beck G with trivial omega and another fusion category is actually always a bicrossed product. If we already add the omega, there will be complications. It will not maybe be an one of these bicrossed products. And then I just want to mention quickly, and then we can go to discussion. I did have an extra thing, maybe answering your question or not answering your question, but so we wanted to know what about other structures. So we proved that if we start with pivotal or spherical fusion categories, the bicrossed product is again pivotal or spherical. And Jelaki proved that if you have a braiding, which is a natural question, what happens when I have a braiding? In that case, exact factorizations are always very easy. They are the linear product, and the braidings behave well. They projectively centralize each other. So, and maybe I will stop here.
So I can ask my question again about the center?
Yes. So maybe, yeah, it's the question that it's in all these papers when they start talking about exact factorizations, and it's a hard question, and it's kind of in our to-do list. In part, I think that would be very interesting, and I think there is some work by other people. They didn't work exactly on that question, but they work on a question related to another construction that Natalia introduced at some point that I think she called cross categories, in which she tries to generalize equivariantization. Instead of equivariantized by a group, she equivariantized by a matched pair. And we are working on that, on how that construction relates to our, and some people was working on the center of the other. But since they will be kind of a Morita equivalence, I think it will be nice. But I think that could be the most interesting. One comment is that from here, I would say that it will not, I don't know. I mean, the modular yeah, I think it might be related to the center somehow, but you need to do the centers of the things, but you need to do something.
Some extra operational.
Smarter.
And the other question is about fiber functors.
Yeah, okay, I will go to my next slide. So these are the follow-up ideas.
These are obvious questions physicists ask.
Yeah, so maybe let me say a couple of follow-up ideas and we can. So braiding is too easy. So what about G-cross braiding? We are working and we have a nice direction, generalizing this semi-direct product that I talked before, the one of C semi-direct product G. With this construction, we can generalize it to something like A semi-direct C, another fusion category, and that is helpful for the G-cross braided exact factorization. And then with my grad student Abigail Watkins, we're thinking, I mean, I put module categories there, but it's actually your question. We're thinking about functors out of a bicrossed product. What are the possible functors? And then if you specialize in VEC, you will get the fiber functors, and if you specialize in M, you will get module categories. And basically, we're able to construct all of them. This is in progress to give you the characterization for module categories or for Hopf algebras. But what we can say is how any functor out of an exact factorization looks. And basically, it's constructed by functors from one of the categories and the other to the same target, and then something that intertwine images of one and images of the other. So you need to have some nice isomorphism with the action of the group also involved and some diagrams. But it's a nice, it's a clean, so you can say very well, and then when we specialize, we will be able to give module categories and Hopf. Yeah.
Okay.
I want to ask maybe the examples, like the A and C are both G-graded fusion category, right? So for example, the TY category, do you use this construction to get new, like interesting fusion category?
Okay, this word new is a hard word because, so in the paper there are examples on how exact factorization of a pointed category and a Tambaya-Miami category will look, and two Tambaya-Miami categories. I'm not 100% sure if they are exactly new, I think, or sometimes saying new is hard because some things are, I don't know, weakly group theoretical. So there are characterizations. You might know, oh, it's rep H for something, but then you don't have the concrete data. So if you check the paper, the last section is about examples. We have concrete data how you can, using by characters, co-cycles, things like this, write the associativity. So we do have the concrete data. I don't want to say the word new yet because I mean, probably in the first version of the paper says new, but then we changed it because I cannot say now that it's new, but okay.
Okay, and another question is that for Hopf algebra, you mentioned there is also this definition for matched pair. Does that give you this like the exact factorization for fusion category?
So it's related to that, and actually that's why we were in part thinking about, I mean, it's a natural question in general, but we wanted to measure there because in that definition of Hopf algebras, they do play with co-cycles. And we wanted to see because I think we will get, that's why we are doing the project with Abigail. We want to see if we really get them all or if we are missing something and we could add extra data in some way. But yeah, we want to know if we get all of them.
Okay.
And you mentioned that this structure behaves well with respect to other structures, this construction. Have you looked into unitarity?
I can check, but I think I didn't check it, but I think unitarity should be good. I think so. I think unitarity should work well. But I don't say that it works well with everything, like with other constructions. I'm not sure. A lot of the projects are like that, about, okay, what will happen in a G-crossed category, and then if I equivalentize, what I will get. I'm not sure how this will relate with the G-crossing. For example, we were able to prove that if you have this G-cross, the two fusion subcategories inherit the G-crossing with their universal grading group. So we did prove a lot of things, but I'm not sure. And being the universal grading group was key. When you lose that, not. But things that are Grothendieck invariant, or some of the properties, pivotality, sphericality, that worked. But I don't know if everything. I think unitarity will be, pseudo-unitarity will be fine, and I think unitarity. Yeah.
Since you also worked a lot on fusion 2 categories, and now there's like a classification thanks to your paper, is there a story there as well that you can take 2 VAC Gs and do some operation on them?
To be honest, I'm not sure. I know that in one of the papers of Matthew and Thibault, they used, or I think it's Matthew and Thibault now, they used these match pairs to construct some of the things. I don't remember if it was in the Tambaria Magami paper or in some group theoretical. So they used the match pairs, but I haven't seen how, that will lift yet.
Structure lift, okay.
But that could be cool, yeah. Oh.
Oh, okay, it's come back. Any more questions?
Come back.
So for these Hopf algebras, I can do this bicrossed product also, and I get this Drinfeld double. Like if I take the rep, does that factor through? Or
for that one, it's better to. You need to think about co-rep, like co-modules. For like some of the things work better for co-modules and modules. In that, because otherwise the exact, like the definition in Hopf, to translate to this one, we need to look at co-module, otherwise it's not working well. But yeah, you will recover some of this using the co-modules.
Okay. No more questions. All right, let's thank Julia again.